introduction that include composite content with state of the problem, objective, and literature review. The second one, I will inform you material properties and method condition. The third one, graph and figure were explained. And the last one is summary of the researcher. Let's start content with introduction. What is hydrogen? Hydrogen energy is a clean energy and non-toxic energy carrier, and it is considered in the future for transportation and industry. When hydrogen is used in the fuel cell, it generates electrical energy with higher efficiency around 40 to 60%. The improvement of a safe, reliable, compact, and cost-effective. Hydrogen storage technology is one of the most technically challenging barrier to the widespread use of hydrogen gas as a form of energy. Nevertheless, methods for hydrogen storage are important for the hydrogen transport and use and shall be carefully considered because hydrogen is sensitive to air and can be exploded. Hydrogen storage technology can be divided into four main categories. For example, compressed hydrogen, liquid hydrogen, chemical hydrogen, and solid hydrogen storage. We will focus complex metal hydride in solid hydrogen storage because the material can reversibly absorb and dissolve hydrogen gas in atomic or molecular form in its structure. The material in complex metal hydride group can be lithium aluminum hydride, sodium aluminum hydride, lithium amide, and much more. This metal group has gravimetric density and properties that are feasible for hydrogen storage. Lithium aluminum hydride was focused in this research because it has high gravimetric density of 10.6% weight and decomposition temperature around 150 degrees Celsius. Several materials in metal hydride can be synthesized by different methods, such as ball milling and sputtering, and much more. Therefore, in this paper, we study the condition of deep coating method to deposit lithium on gas substrate. The deep coating condition that provide the least oxide was saw in this work. The results are going to be used in the future work where oxide-free lithium aluminum thin film is targeted. The oxide thin film will have high hydrogen storage efficiency due to the absence of oxide. The oxide is undesirable as it reduces the ultimate hydrogen yield. The second part as material and method. 2.1 Material using in this paper such as lithium aluminum hydride, tetrahydrofuran, dimethyl ether, gas substrate, nitrogen gas, and pyrite bottle. 2.2 Sample preparation. Gas slides were cut and ultrasonically using acetone and followed by isopropanol. The gas substrate were heated in a controlled humidity and in the atmosphere groove box before thin film deposition. 2.3 Lithium aluminum solution preparation. All gas slides were dyed before using. Lithium aluminum powder were mixed with solvent in the pyrite bottle to the solution. After that, the mixed solution was ultrasonically stirred, then it was magnetic stir at room temperature for the overnight. 2.4 Lithium coating and post annealing. The deep coating was performed at room temperature for 10 times. Subsequently, the thin film were post annealed in a groove box immediately after the position. 2.5 Phase enzyme and surface morphology analysis. The phase of thin film was characterized using X-ray powder diffraction. The crystalline organ size was calculated from shear equation, scanning electron microscope used for surface analysis. The third part as result and discussion. 2.1 Influence of lithium concentration. The figure 1 illustrates the XRD pattern of deposit lithium thin film, which were deep coated in the lithium concentration of 6 gram per liter, 10 gram per liter, and 20 gram per liter without post annealing. It is obvious that the most of lithium aluminum hydroxide hydrate peaks is higher than every peak include the lithium aluminum hydride peaks. This implies that the deposit lithium were oxide to lithium aluminum hydroxide hydrate. The intensity ratio of 002 per 003 peaks determine the least oxide on the surface of thin film. When considering the intensity ratio, the highest ratio peak is sample dip coat in the lithium aluminum hydride of 20 gram per liter as shown in the figure 1c at the ratio of 0.725. The figure 2 when considered same analyzed and XRD graph from both figures. It was found that the lithium concentration of 20 gram per liter has dense surface morphology and less pore with the gain size. When considering the each gain size of lithium concentration, the highest gain size is 713.89 nanometer, with dense surface morphology. The last gain size enhances the kinetic of hydrogen solid, in which results are compiled with the XRD. 3.2 Influence of post-annealing time on lithium thin film. When considering the figure 1, the lithium concentration with the post-annealing time, the peak intensity of lithium aluminum oxide, hydrate of every deposit, lithium concentration decreased with post-annealing time. The peak intensity tend to be more comparable with the peak intensity of lithium peak when the post-annealing time increase. The highest ratio is at the lithium concentration of 20 gram per liter and 60 minutes post-annealing time. In general, post-annealing time improves the property of thin film. Therefore, the lithium concentration of 20 gram per liter with post-annealing time at 60 minutes is the most preferred condition to produce hydrogen storage. Figure 3 shows the same image of surface morphology of deposit lithium thin film at the concentration of 20 gram per liter with various post-annealing time. When considering the pore of thin film, the lithium concentration of 20 gram per liter, the dense surface without any crack was improved, increased the post-annealing time. The gain size of the deposit thin film with the post-annealing of 60 minutes is 807.14 nanometer. As a discussion previously, the large gain size improved the kinetic of hydrogen storage. The last part as result and discussion. The deep coating method was applied to deposit lithium on gas substrate at various lithium concentration and post-annealing time. The lithium aluminum hydroxide hydrate peaks was detected on every sample with various peak intensity. From XRD result, the highest lithium peaks and the lowest lithium aluminum hydroxide hydrate peaks were found in the sample with deep coat in the lithium concentration of 20 gram per liter. In this sample, the surface gain size was the largest and no crack on the thin film surface was observed. Moreover, when considering the post-annealing time, the lithium aluminum oxide hydrates tend to decrease with increased annealing time. The lithium concentration of 20 gram per liter with post-annealing time at 60 minutes was found to be the most preferred condition in this study. These oxide contaminants shall be totally removed in order to produce thin film with be an efficient hydrogen storage. Thank you for your attention. Are there any questions?